So we've taken our weights, we centered them, divided by standard deviation, and what we got are our weights in so-called standard units, where we subtracted or removed any influence of the position and the width of the original distribution. Standard units are very useful, okay, because it allows us to answer questions about probabilities and proportions without actually having to count the data itself. Basically, once I know the mean weight and the standard deviation weight, I can forget my histogram. I can forget all of the data set and just refer to that normal curve. So it's very efficient then. I can forget all the data. All I need are those two numbers. So for instance, you might be interested in what's the proportion of weights between 200 and 225. Another way of kind of framing this question is, what's the probability that a randomly chosen person from this data set is between 200 and 225? Now, if I have all of the data, I could just count, right? I could just count how many people fit within that range and then divide by the total number of people, and that gives me my answer. But suppose I don't want to count. Suppose there are 1 billion people and I don't want to go through all of them. But I do know I know the mean weight and the standard deviation. I can use that to figure out the proportion because I know that that histogram is normal. That's a very key assumption here, is I know that that histogram is approximately that normal bell shape. So how do I go about doing this? What I want to do is I want to calculate the area of the distribution in this interval, okay? And I'm going to do that without referring to the actual data that generated the histogram. I'm going to go back to the curve. I want to figure out the area within a certain interval of the curve. Basically, you can think about taking this curve, this standard normal curve, squashing it and centering it so that it overlies this distribution, and then figure out the area under that squashed curve. So what are my endpoints here? I want to calculate the area under the normal curve using SciPy Stats Norm CDF, but what do I plug in? What's my right endpoint? What's my left endpoint? What I need to do is I need to take the weights and convert them to standard units. So here's how I do that conversion. We did it before, but here it is in a simple formula form. If I'm trying to convert a single weight to standard units, I take that weight, subtract the mean, and divide by the standard deviation. Okay, so I have a weight of 225. I want to convert that to standard units. I take 225 minus the average weight, and I divide by the standard deviation of weights. Now, this function here is a useful one to remember. It's pretty simple, it's pretty intuitive, but nevertheless, make sure you remember it. It's just our way of mapping a number to standard units. Now, once I've done that, it turns out, as you can prove, if a distribution, if my histogram is roughly normal, then the area between A and B in the histogram will be pretty close to the area between ZA and ZB in the standard normal curve. So ZA being A in standard units and ZB being B in standard units. So let's take a look. I have 225, a weight of 225. I want to compute this number in standard units. So I take 225 minus the mean weight, divide by the standard deviation. I get 1.92. So we say that 225 in standard units is 1.92. So another way of interpreting this number is that 225 pounds is 1.92 standard deviations above the mean. Okay, so standard units, right, are really useful, because if I tell you that somebody weighs 225, you don't have any information about whether that is an average weight or if it's above average or below average. You don't know, but standard units tell you immediately. It says 1.92 standard deviations above the mean. So standard units tells you how far away are you from the mean. Okay, so let's take that and compute the area between 200 and 225. So I found my right endpoint, right? 1.92 is my right endpoint. My left endpoint I get by taking 200 minus the mean divided by the standard deviation, and I get 0.65. Okay, so this number I interpret as saying 200 is 0.65 standard deviations above the mean. Now I want the area of the normal curve between 0.65 and 1.92. So I use SciPy norm CDF. So I take CDF of 1.92 minus CDF of 0.65, and I get 0.22. So that tells me that approximately 22.8% of weights are between 200 and 225. Now I calculated this without ever actually counting how many people were in that portion of the histogram. Now I could go back and actually do that. Let's do that here in a second. But just to give you a picture of what I've done is I found the weights in standard units. So I took 200, converted it to standard units. I found that it was about here. Took 225, converted it to standard units. I found that it's about here. And then I found the area of the normal curve in this interval. So let's check and make sure that that actually worked pretty well. So what I'm going to do is I'm going to fall back to my technique that uses the data. I'm going to take my data set. I'm going to do a simple query on this to find all of the people whose weight is greater than or equal to 200 and less than or equal to 225. And then just count how many there are and divide by the total number of people. And I get 0.2294 or 22.94%. Remember what we found on the previous slide using SciPy norm CDF was 22.84. So really, really close. Okay. And just using the normal distribution and the mean and the standard deviation, I didn't have to go through and perform this query and count. Okay, so it was great. So in summary, if I know that a distribution is approximately normal, meaning it has that bell shape, and I know its mean and standard deviation, I don't actually have to use the data itself to compute percentiles. I can use SciPy norm CDF, or in general, the CDF function. Okay. Now, let me go back to something from last lecture, Chebyshev's theorem, Chebyshev's inequality, and compare it to what we just learned here. So remember, Chebyshev told us something very similar to what we're learning here. It said that if I know a standard deviation, then at least 1 minus 1 over z squared % of the data are within z standard deviations of the mean. Okay. And now I've learned this, it tells me that, okay, well, I can compute it with SciPy norm CDF. So what's the difference? The difference, remember, is that Chebyshev assumed nothing about what your histogram looks like. It doesn't assume that I have a bell curve. Okay. The normal curve is giving you much more information. If I know that my distribution looks like a normal curve, I can say more than Chebyshev's inequality. So for instance, Chebyshev's inequality says that if I plug in 1 into this function, right, I get the statement that at least 0% of your data is within 1 standard deviation of the mean. Remember, Chebyshev doesn't know your distribution, so it can't say anything more than that. But if I know my distribution is a normal curve, or approximately a normal curve, I can say much more. I know, remember a few slides ago, I said that approximately 68% of the data is within 1 standard deviation of the mean. Similarly, Chebyshev says, well, at least 75% of your data is within 2 standard deviations of the mean. Remember, it says at least, okay? The normal curve says, well, it's pretty much 95%. It's not at least 95%, it's approximately 95%. And for 3 standard deviations, Chebyshev says at least 88%, normal says almost 100, 99.73. Notice that this isn't saying Chebyshev is wrong. Chebyshev says at least. So the normal, if you look here, is always greater than or equal to. It always satisfies Chebyshev. But if I if I know my distribution is normal, I'm going to use these and not Chebyshev. The power of Chebyshev's inequality is if I know nothing about the data and the distribution, or it's a weird distribution that doesn't look anything like normal or doesn't really have a name, these things still apply.